Hello, my name is Andrew Emerton, and my teammates are Daniel Cortez and Javier Echeverria, and this is our Johnson & Johnson capstone project. Special thanks to Dr. Christensen and Bill Femmer for their gracious guidance throughout the course of this project. Here is the agenda for this presentation. The Oculus Quest is a virtual reality headset that allows users to run applications on the device. It also has two controllers, which allows users to interact with objects in the virtual environment. A-Frame is a web framework for building VR experiences that can be ran in a multitude of places, including the Oculus Quest's virtual reality browser. A-Frame also uses the WebVR API to gain access to the headset's sensors. This allows it to render content directly to the Oculus Quest. MRI scans are used to form detailed images of the body. These are typically in a series of 2D slices. Johnson & Johnson is an American corporation that is most known for their development in medical devices, pharmaceuticals, and other consumer packaged goods. Our problem. Can MRI scans be visualized using off-the-shelf VR technologies such that the MRI 3D model can be rotated, scaled, and cut on any plane in collaboration with other people in remote locations to be able to locate and characterize abnormalities in the scan? Our requirements. As a user, I want to be able to upload my MRI images to be converted to a 3D model. Our ability to take 2D MRI images and form them into a 3D model that can be hosted in a virtual environment will be a crucial requirement for this project. As a user, I want to be able to see the other people in the world around me and their interactions. As a user, I want to see the abnormality inside the 3D scan so that I can easily identify a tumor. The main idea with this project is that it should be easier to find and locate issues within a 3D model versus just the 2D scans. As a user, I want to be able to move, resize, and cut a 3D model in VR. In order for users to efficiently locate issues in this 3D visual representation of the MRI scans, it is crucial that they are able to manipulate the model in this environment. They'll be able to do this with the two controllers that are provided with the Oculus Quest.
One of the bases of our project is converting 2D MRI images into a 3D object. We do this using marching cubes, which is a iterative algorithm used to create triangles or voxels. It does this by having multiple points on the cube, as defined like in the name. And what it does is an image is actually just a 2D array of integers or floats. So what it's doing is it's marching the cubes over the array and finding where there's close points. And that's how it knows to put those two together. And when it does, then it makes the triangle. To do this, we are using Scikit's marching cubes algorithm, and we are also using PyDICOM, which allows us to select values for different types of like flesh, such as organs or bones. The next step would then be importing our MRI 3D model into A-Frame. This would either be done by calling a JavaScript command that would run our Python code on the device, or we would have to run it off-site, like on AWS or another computer. This is because the headset runs off a Snapdragon processor, which is usually used for phones. So it may not have the horsepower to actually compute the conversion of MRI to 3D. The pipelining could either have a UI inside the headset, or we could put it on another computer so that the user would then upload its images, convert it, and then put on the headset. So then it would have the 3D model right in front of them.
Another aspect of our design is that we have to be able to interact with the object within the 3D virtual environment that we have created with A-Frame. Now, what exactly do I mean by interact? We define interact by three different functionalities: scaling, splicing, and repositioning. When we say we want to splice the 3D object, we want to be able to divide the 3D object along its Y or X axis to be able to observe the contents of the inside of the 3D object model. When we say we want to be able to scale the 3D object model, we want to be able to change its size to make it either larger or smaller depending on the user preference. And finally, when we say we want to be able to reposition the object or move around, we want to be able to grab the object with our controllers in the virtual environment and reposition it along the X, Y, or Z axis to wherever the user defines. The benefit of using A-Frame as our chosen web framework is that with A-Frame we can support a variety of inputs. What this means exactly is that we can accept inputs from the user through a VR headset controller, such as the Oculus Touch or Go controllers. We can also accept input from mouse and keyboard, and even we can accept input from mobile devices in the form of touch controls. A key aspect or design of our project is that we have to have the capability of collaboration on A-Frame. What do I mean by collaboration? For us, collaboration means in the hosted virtual environment, multiple users should be able to see each and every user that is in the environment and their corresponding interactions as well. This should be applicable no matter the device that you are using to access this hosted virtual environment. As you can see in the screenshot below, I have here a hosted environment in A-Frame, which I'm accessing as three different users from 1, my laptop, 2, my phone, and 3, a desktop. As you can see from the image, all users can see each other, and more importantly, all users can interact with each other in real time. Real time means that all interactions or all events that happen in this hosted virtual environment happen synchronously across all devices to all the clients. Among the other interactions that users can have in this virtual environment include seeing and hearing other users. This is provided by the built-in functionality that is included in Networked A-Frame, a GitHub library that allows you to host these environments.
The biggest constraint on this project is the headset itself through its hardware. Like I mentioned before, it is running a Snapdragon processor, which is a Snapdragon 835, which is 2 or 3 years old. Not only that, but the device only has 4 gigabytes of total RAM for the whole system. One of the things we ran into were that sometimes it could go up to 6 to 8 gigs of RAM that is being used when running marching cubes, so that would be a big obstacle. Not only that, but the Snapdragon 835 may take a considerable amount of time to process marching cubes, as on a laptop, for example, it already takes about 2 or 3 minutes. Our other constraint is cost, being $400, so that is because the user would then have to spend at least $400 on at least one headset, and another if they wanted to work in collaboration with someone.
In our project, there are many applicable standards that apply to the various technologies that we use. In this first point, marching cubes is a computer graphics algorithm that was developed by William Lorentzen and Harvey Klein as a result of their research at General Electric in 1987. As a result, this is the most widely used implementation of marching cubes. You can actually pay a royalty fee to use this algorithm for your own purposes. This standard is maintained through the patent that was patented back in 1987. The second point is HTTP, JavaScript, Python, and HTML. All of these languages, with the exception of HTTP, which is a protocol layer, are maintained and have a standardization by various organizations that correspond to each language. For example, JavaScript is maintained and has an applied standard that is set by ECMA. HTML and HTTP have standards that are set by the Worldwide Consortium. DICOM is the standard for communication and management of medical imaging information and related data. This was developed by the National Electric Manufacturers Association, which holds the copyright to this published standard. And finally, WebXR is another platform that has applicable standards, and it is maintained by the World Wide Web Consortium organization as well.
So for our risks regarding the project, we have four risks mainly, which are time, the technology we're using, the hardware, and the scope of the project. Time is due to us receiving the headsets later than we would have liked, which means now we are beginning to actually use the headset and test our project. A-Frame and WebXR are both new technologies, so documentation is low, meaning that we may have to either research more or build things from the ground up. Like I previously said, the hardware is not the greatest and may take long to process marching cubes. And the last one is scope, which is making sure we do not stray from the requirements and guidelines that we were given by Johnson & Johnson.
As you can see from this Gantt chart, we are taking a multi-phase approach to development for the rest of the semester. From August 28th to September 14th, you can notice that this period of time is marked in yellow, as it defines the period of time where we did not have the necessary hardware or tools to actually test code or do any deployments to the headset. Instead, we focus on defining project requirements and researching relevant tools and technologies for possible implementation. Last Friday, we actually received our Oculus headsets. So starting from that point on now, the development is splitting into 3 different development paths. One path will be solely focusing on testing the Marching Cubes algorithm in order to observe average rendering time and improving performance through different techniques. The second development path is focusing on VR interactions between users, allowing them to be seamless and also define UI and how these interactions occur with 3D model objects. The third path is focused on networking. This is a crucial path as well because we have to focus on getting all events synchronized in the virtual environment so that all events that happen occur to every user at the same time. Finally, we will all develop the pipeline to move the 3D model that resulted from the Marching Cubes algorithm into the A-Frame virtual environment. Between October 5th and November 9th, between November 16th and November 30th, we will solely be focusing on debugging and making any functionality, additional functionality or accommodations that are approved by Johnson & Johnson.